Thank you, Ernie. I'm going to try to make this very quick because I don't want anybody to miss out on their first drink at 5 o'clock. I want to talk about the last five talks or four talks was about technology. I'm going to talk about an application for titanium. Tricor Metals is an industrial fabricator. However, we got involved with this application, which is a little bit different than your normal aerospace. You're talking about planes that go 600 miles an hour. We're talking about something here that's going to go 430,000 miles an hour. And we're also talking about something that's going to go 93 million miles away instead of just 60,000 feet.
NASA's Parker Solar Probe mission is about to embark on a historic journey to our very own star, the Sun. Named for Dr. Eugene N. Parker, whose contributions have revolutionized our understanding of the Sun, Parker Solar Probe will usher in a new era of exploration. It's a mission of extremes. The spacecraft will plunge through the Sun's atmosphere, called the corona, and fly closer to the Sun's surface than any spacecraft in history. More than 7 times closer. The Sun's surface is hot, at temperatures exceeding 10,000 degrees Fahrenheit. But the real surprise is, its atmosphere is even hotter, 300 times hotter. Facing the corona's brutal heat and radiation conditions, Parker Solar Probe will finally provide answers to some of the most important questions about how our Sun works. As Parker Solar Probe speeds around the Sun making these measurements, it's moving at over 430,000 miles per hour. That's like traveling from New York to Tokyo in less than a minute. This mission is the culmination of 60 years' work by the best and brightest scientific and engineering minds. Today, our technology will let us achieve our dreams, to reveal the secrets of the corona and our Sun, and to one day help better protect technology from the threats of space weather. In 2018, we will launch Parker Solar Probe, humanity's first mission to touch the Sun.
But anyhow, it was built by Tricor Metals in Worcester, Ohio, and it was designed by Johns Hopkins Advanced Physics Lab in Maryland. Project and my co-authors, Brandon Clark was the project manager at Tricor Metals, and Timothy Cole was the lead mechanical engineer, design engineer at Johns Hopkins University. And as I said, it was named for physicist Eugene Parker, who predicted the existence of the solar wind. This is a 7-year mission, 24 orbits. It started about 2 months ago, and it will end in 2025. It will go, the closest it will go is 3.83 million miles from the Sun, and again, it'll be the fastest man-made object. Sorry. This is just a small representation of the whole Parker Solar Probe. And you can see the titanium. There is a, oh, here it is. You can see the titanium truss structure right in this area. And I'll talk a little bit more and I'll show some more pictures of that. There we go. This is the titanium truss structure. It is all titanium grade 5. It started out in 2012 with titanium 9 and titanium 12. And over the course of about a year with Tricor Metals and Johns Hopkins talking, we went back to all titanium grade 5. And these are all pipes or tubing, and then there's some castings and forgings on the edges, and we'll show that a little bit more in a couple of minutes. Okay, as I said, We started out with grade 9, went to grade 5, a 12-month design period. When we finally got the design down, the key areas there were the weight, because we had to blast it off the Earth and get it into orbit. The strength to mass, because we wanted it to be able to hold the heat shield on the top and then hold the rest of the satellite on the bottom. The exacting measurements and angles, because we don't want to have it moving and have the satellite ending up outside of the umbra of the heat shield. We wanted the heat shield to protect from the sun. And then also that dimensional stability. Like I said, we started the discussions in October of 2011. We finished the initial design in 2012. We shipped the first unit in April of 2013. That was a no-fly unit. That basically went through all the tests that anybody at Johns Hopkins and the Goddard Space Center could think of. And then they finally decided on the final design, and then we shipped the final 2 flight units in April and July of 2016. The weight of the structure was 55 pounds. The height was 47, a little under 48 inches. The top diameter was 70 inches. Bottom diameter was 40.6 inches. So basically you had something that was coming in this way, and the bottom structure was the same diameter as the rest of the satellite. The critical aspects was the titanium grade 5 because of the weight and the strength to weight ratio, and all the angles and measurements. And all that was related to the mass and the stability. And one thing I have to say, I don't know how many people watch The Big Bang Theory, but the first time we went down to Johns Hopkins, the design engineer, Brandon, and I sat in a room with about 15 physicists. And it was like talking to Sheldon Cooper of The Big Bang Theory. It was all way up here, and we had to get them down. That's why it took us a year to get the design down. Excuse me. This shows some of the attachment points, these TPS attachment points. That's where the thermal protection shield will be attached. And then down below, whoop, I hit the wrong button. Where'd I go? I'm going the wrong way. Sorry. There we go. Down below is where the satellite will be attached, and we'll show a couple pictures of that. Fabrication process, basically a lot of machining on the forgings and on the ends of those tubes. We had to do chemical milling of the tubes because of the mass requirements, the weight requirements. We couldn't have a tube that was just manufactured. We had to make it exactly the right thickness, exactly the right mass. We did all our welding by hand TIG with an argon shield, and you'll see something about that in a minute. And then the positioning, because it was so critical, all those angles in that were a little bit different. So we had to use a Faro positioning measurement device, which allowed us to get 3D measurements to make sure everything was in the proper place. This shows some of the machine fittings. Some of the ones on the left are for the top, where the thermal shield goes on. The ones on the bottom are for the bottom of the TSA, where the satellite and all the equipment goes on. And this shows you the chemical milled tube. You can see the outside, the ends of the tube are slightly thicker than the middle of the tube, and we found a place in Pittsburgh that did this for us, and it worked out very fine. This is all 6th floor, if you remember. Now here's a picture, excuse me, of the TSA in the steel fixture. And one of the things we had to do in talking with Johns Hopkins, we had to make sure, like I said, that this was built exactly to dimensions. So we needed a steel fixture. Between us and Johns Hopkins, we had one built, and then that helped us to maintain all those angles. On the bottom here, you could, whoop, again, I'm hitting the wrong thing. You can see some plastic tubing, and what that is, that's allowing for argon shielding on the interior of the 6/4 tubing for while we're welding. So we had back shielding as well as the front shielding of the welds. Just to show you some of the welds here, Tricor Metals welders are very good, and this is typical of our welds. And again, all of those angles were critical, and here you can see some of these angles were really kind of strange, and not too many of them were alike. So it was very difficult to make sure it was positioned properly when it was just set in there, after it was welded, and during the final assembly and before shipment. And here is the picture of the truss support assembly ready to be shipped, and you can see the top section, and again, all those different angles.
Right now we're at Tricor Metals in Worcester, Ohio. We're a titanium fabrication company. We primarily deal with heat exchangers and pressure vessels for chemical companies. This TSA Solar Probe Plus program structure is towards the end of its, fabrication process. We're within a couple weeks of shipping to Johns Hopkins, and we're proud of it. And it's definitely something that we don't do every day, so we're excited to do it.
The reason that this truss is made of titanium is because we need to limit the heat from the heat shield that gets down into the spacecraft. The Solar Probe Plus spacecraft is protected by a shield that mounts to the top of this titanium welded truss. That shield provides a shadow that the rest of the spacecraft hides behind when we get to our closest approach to the sun. At that point, the top shield will be at 1200 degrees Celsius. If you go outside this afternoon, on a nice sunny day, you're in a one sun environment. Solar Probe Plus at closest approach is in a 500 sun environment. So if you consider what it would be like outside with 500 suns in the sky, you can then understand how the front of this shield will get so hot, and we can't afford to let all that heat get into the spacecraft.
The testing at Johns Hopkins APL required vibration testing to make sure the strength of the welds, the strength of the system, and the workmanship. It also required thermal vacuum to give it an idea of what was happening in space, if it would move in a thermal vacuum, and acoustic testing, because during launch, that's going to undergo a lot of vibration. You want to make sure that nothing moves so that your satellite is still going to be protected by that heat shield. This just shows two pictures of vibration testing. The testing was done on the titanium truss structure by itself, and then with the whole satellite put together. The red stuff on top there is basically mimicking what the weight and distributional weight would be for the carbon heat shield. That doesn't go on the final satellite. Just a picture showing the thermal vacuum testing, and again, this shows the titanium truss section undergoing the thermal testing, and then here showing this is a vibration test with the heat shield on the titanium truss. And a couple other pictures just showing the final assembly. And on the left-hand side, you can see that what amounts to basically the whole satellite with the heat shield, the titanium truss section right here, and then the rest of the satellite. There are some instruments that are up in this area. But most of the instruments are down here, and then this is the rocket motor that's going to give it its final boost. But the first video said it was we're going to be going to the sun in 2018. Well, it lifted off at 3:31 on August a.m. on August 12th, On the 2nd of October, it did its first flyby of Venus, and it has to fly by Venus 6 times in order to slow it down, to take it into a spiral towards the sun. And the last time it's going to go past the sun, it will be at 3.83 million miles and going 430,000 miles an hour. Basically, just to give another representation of the solar, come on, there we go. The probe, again, here's the truss section. You're looking, this is protecting it. This is going to keep it at temperatures that the instruments can still work, while the outside temperature is going to be roughly about 1600 C. And if one of the things that it's going to see, if you go outside right now, there's one sun. If you go out, when this is 3.83 million miles away, it'll be like having 500 suns in the sky. So you can tell how much difference heat and radiation it's going to see. So we're hoping that in 2024, 2025, that we'll be able to see this go past the sun and get all kind of good information off of the sun because of that. And again, I want to thank my co-authors, and I'll take any questions after we're done. Thank you.